Hello everyone, my name is Professor Polish, and in this section I'll be giving you an overview on slurries and why they are a critical component in the manufacturing of chips. Slurries are water-based solutions that contain proprietary chemicals and abrasive nanoparticles. They are used in the manufacturing process of semiconductors and other electronic devices. Slurry abrasives are typically made up of silica, ceria, or alumina particles that are blended with other chemicals specially formulated for each different polishing application. Slurries are a fundamental component in the CMP process. This slide is a general CMP slurry composition. Slurry consists of abrasive nanoparticles for mechanical abrasion, along with a variety of organic or inorganic acids or bases for controlling pH, dispersants to prevent agglomeration, corrosion inhibitors, surfactants, oxidizers, chelating or complexing agents for controlling removal rates and transport, and biocides to keep it all from spoiling during handling and storage. The exact composition of slurry is very dependent on the specific application, and we have hundreds of different products to accommodate the needs of our customers. Here are some of the nanoparticles we use in our slurries, commonly silica, alumina, and ceria, and generally 100 nanometers or smaller in size, about the same dimensions as the components we are polishing. Silica, or silicon dioxide, comes in many shapes and sizes. Colloidal silica is often spherical, but can clump like microscopic cocoons. The particles can be all one diameter, that is, monodisperse, or a mix, polydisperse. Colloidal silicas are usually made from sodium silicate, or TMOS, tetramethoxysilane. The raw materials our suppliers use have a big influence on the particles they produce. Silica can also be crystalline like quartz or fractal like a snowflake when produced as a fume from burning silanes such as tetrachlorosilane or methyl trichlorosilane. Most of our early products employed fumed silica and fumed alumina, but now we are using a wider range of engineered nanoparticles to improve cost, quality, and performance. Depending on how and where the silica is made and from what raw materials it's made can make a big difference in how it performs in a slurry. And that's just silica. The same things can be said for virtually every nanoparticle. The surface area of a particle can also be important. 1 kilogram of our fine silica or ceria has as much surface area as over 15 football fields. Remember that the key role of the particle is mechanical. The rolling, bouncing, sliding action of the particle wears away the surface. Sometimes the particles have special chemical properties as well. This is an example of how ceria, cerium oxide, behaves with a special chemical affinity for polishing silica. Some researchers call ceria polishing the chemical tooth because they believe it takes a bite out of the silica surface. But mostly particles are believed to be mechanical, rolling and sliding on the surface like sanding wood. In a purely mechanical polish, the removal rate is usually linearly dependent on both the pressure and sliding velocity. This is the well-known Preston equation, and it makes intuitive sense. The faster you slide and the harder you press down, the faster you polish. Some CMP slurries are non-Prestonian, indicating a stronger chemical dependence. The slope of the curve is dependent on the constant Kp and varies a great deal among the various slurries and pads and surfaces. Now let's talk about the chemicals in the slurry. The role of the chemistry in CMP is really complicated, as we alluded to before. If the surface of the wafer is very hard, chemicals can serve to soften it to make it polish faster. If the wafer is too soft, we can employ certain chemicals to form a protective skin to make it seem harder. We can take highly reactive surfaces and protect them from corrosion using chemical inhibitors. We can use chemicals to influence the rheology or friction at the interface between the pad, slurry, and wafer. We add chemicals that modify the pH because some surfaces polish better under acidic conditions and others under basic conditions. Most of our particles and surfaces carry intrinsic electrical charges, some positive and negative. Chemicals can be added to adjust the charges to make the components attract or repel one another. Often we employ chemical oxidizers or oxidation inhibitors to influence the rate of polishing. Many of our researchers have spent decades studying the chemistry of CMP because this is often where the difference between a successful process and a failing process occurs. Another concept that you might encounter is called planarization efficiency. It is a measure of how efficiently the rough surface becomes flat. The cartoon shows the concept of planarization efficiency, which is the ratio of removal rates between the active area and the field area, or between the highest overburden area and the lowest overburden area. For example, if the polish rate at the top surface is the same as the polish rate in the valley, the planarization efficiency is 0, meaning that the step height difference is maintained even after long polishing times. If the top polish rate is high and the valley polish rate is low, the surface can easily become flat within short polishing times, so that the planarization efficiency increases. For example, if the polish rate in the valley was 0, the PE would be 100%. The most common mechanism of many reactive metals CMP is more chemically driven. Once metal surface is exposed to the slurry, the metal surface quickly gets oxidized by either the water or an added oxidizer like hydrogen peroxide. The oxide often protects the metal from further reaction, but through the mechanical action of CMP, the protective oxide film is removed by abrasive particles. When this passive film is removed, new passive film is generated and removed in turn. This basic sequence of oxidation and abrasion keeps repeating until the operation is stopped. Sometimes this doesn't always work as planned, especially if some parts of the metal surface are more reactive than others due to strain, grain structure, or local impurities in the metal or alloy. Then we might have to employ special chemical additives to control the process. Let's give a couple examples of chemicals we add to the slurry and their role. Here we illustrate corrosion and the role of etch inhibitors in the metal slurry. Let's say we wanted to polish the metal in the first picture on the left, and we wanted to stop polishing when we got to the oxide, just like on the last slide where everything worked perfectly. This is often the kind of problem we face. If we were to make the slurry with particles and some acid and some hydrogen peroxide, it's very possible that the slurry would etch a pit into the metal surface, as in the middle picture. Maybe you have seen corrosion on your car or on tools that have been left outside. By adding an inhibitor, as in the right image, we can protect the surface from pitting. But you better be careful. If you add too much inhibitor, you might make it impossible to polish the metal to begin with, or slow the polishing rate down too much. Many metals are extremely susceptible to acid pitting corrosion, especially at knit lines where the metal deposition process grows from the edges in and joins in the center. If there are voids in the structure or just poor microstructure, this can create what we call a keyhole defect, as we will see in the next image. Here you can see how CMP can create or reveal a flaw in the microstructure. CMP is often blamed for creating defects that are actually intrinsic to the metallurgy and the deposition process. In this case, CVD, chemical vapor deposition, was used to deposit tungsten. CVD starts by depositing metals on the walls and working its way in. When the grains grow together in the middle, there are often voids. Other examples of CMP revealing problems include imperfect alloys such as copper in aluminum or silicon, voids from electroplating, or inclusions from debris during the metallization. We'll hear more about defects later. Let's get back to the chemistry of CMP slurries with another example. In this picture, we illustrate the role of surfactants. Let's pretend that in this example, the big blue particles and the gray wafer surface are both positively charged. They will tend to repel each other, which will slow down the polishing rate. If we add a slightly negatively charged surfactant, the kinds of molecules that make up common soaps and detergents, they can act to neutralize the charge on both the particle and the wafer surface and will accelerate the polishing rate. By using surfactants to adjust the charges of the particles, surfaces, and even the pads, we can fine-tune the polishing process so it is not too fast, not too slow, and such that the particles don't stick to each other or the surface. There are thousands of types of surfactants with different charges and sizes that can be employed. This is a specific example of using surfactants to change particle surface charge. In the case of silica wafer polishing with silica-based slurry, each surface is negatively charged and will repel each other, resulting in very low removal rate. If we add an oxide promoter, which creates a positive charge on a particle, it will now attract to the wafer surface and result in high removal rate.
And ready when you are.
Let me summarize where we are so far. By now, you should understand the importance of CMP in chip making, and that the key elements of CMP include a tool, a pad, a slurry, and a process, and that these all work together to achieve the desired perfect wafer. One of the main products that Cabot Microelectronics produces is the slurry. Slurry includes water, nanoparticles, and chemicals that are carefully customized for each of the different designs and materials that make up the various layers that are polished. There are a lot of choices for particles and chemicals, and the CMP process is very sensitive to subtle changes, such as particle size, particle shape, and surface. Particles are largely mechanical in their role, while chemicals seek to fine-tune the removal process to accelerate or decelerate polishing as required. Are you with me so far? Good. Then let's go on to look at the CMP polishing pad.